Let me now change and talk about self-driving cars. Again, in the context of deep learning. Well, self-driving cars have a whole lot of benefits, and we'll talk about it in just a moment. One of its early manifestations is a feature called ADAS. Using various sensors, sometimes using a camera, we can now have driver assistance. Driver assistance basically works by detecting a pedestrian, detecting a car, detecting some lanes, and before you run into the car, before you run into a pedestrian, the car invokes the brakes and stops the car. You could use this basic capability for highway adaptive cruise control. Just follows the car in front of you. If the car in front of you slows down, you slow down. If the car in front of you speeds up, you speed up. And the car in front of you stops, you stop. That basic capability of ADAS is incredibly useful already. However, stopping a car when you detect an object is far from a self-driving car. It's far from a self-driving car. It surely is one step. The question is, how do we get to the future of self-driving cars? Now, one next step, of course, is detecting objects. Why don't you just detect free space as well? Detect free space as well. Well, I think that there's a very big difference between detecting an object and doing something and versus understanding the environment, the context of the environment, and figuring out what to do. Driving is not about detecting. Driving is a learned behavior. Driving is not about detecting. Driving is a learned behavior. Our feeling is the right answer is to augment, to add to today's ADAS systems, to augment today's ADAS systems with a deep learning network. That's our vision for the NVIDIA Drive PX, to augment ADAS. Sure, if somebody detects a car, detects a pedestrian, we ought to stop. That feature exists today. It exists in a whole lot of different forms. I think we ought to continue to let it exist. However, we should augment that system with something that will learn the behavior of driving over time. Will learn the behavior of driving over time, and that could be updated over time to become smarter and smarter and better at driving. Now, our perspective of deep learning's impact in self-driving cars is very similar to the perspective to the events that just happened in the year 2012, the Big Bang. I believe the Big Bang of self-driving cars is about to come. In the next couple of years, because of the availability of massively parallel supercomputers like Digits DevBox, and the ease of training, the availability of data just from cameras like GoPro, we're going to be able to train these networks with better and better behavior, smarter and smarter behavior. But we can't do that by coding it with if-then else's. If I detect this before that, and if it's moving at this rate after that, and every single condition, and program a car and put it on the road and do it over and over again, you'll never get there. And so we believe that the architecture, just like deep neural nets, the Big Bang that happened in 2012 is about to happen here in self-driving cars, and it starts by augmenting ADAS with a deep learning network. Now let me just illustrate a couple of things. This particular road here, the easy thing, of course, is to detect that there's a free space in front of you. But that free space, how you think about that free space, in this particular case, I'll just drive through it. That free space changes. The meaning of that free space changes if all of a sudden there's a bus on the other side. And that even changes. If the bus is driving, so be it. But if the bus is stopped and the light is on, my free space all of a sudden recedes quite far. In fact, that free space changes yet again if a car is parked by the side of the road, but the door is slightly open. If that door is slightly open, I know it's about to become fully open, and somebody's likely to step out, and I should be extremely concerned. The free space is now modified. Now, the world of free space, driving doesn't work like this. And of course, here's an example of a free space that otherwise wouldn't be a free space. It detects for some anomaly that an oil sludge, or maybe it's a hole, or maybe it's a pool of water. For all of us, we would just drive through it. Just drive right over it. If you aim the car properly, it'll just drive right over it. Why stop? Well, the way to think about that is this. How do we think about self-driving, and how do we think about computer code? I think it's going to be very, very difficult to code, write if-then else's, and design feature detectors and condition detectors and scenario detectors of an infinite number of possibilities to go figure out how to ultimately lead to a self-driving car. It's a little bit like this. It turns out that ping pong is one of my favorite games. And here's the question. How do you teach a baby how to play ping pong? Well, if we use conventional ADAS methodologies, what we would do is this. First, we teach the baby how to detect a ping pong ball. When it leaves a ping pong paddle. Let's go ahead and run that video. How it leaves the ping pong paddle. But that's just the beginning. That's just detecting. This is real. That's just detecting the ping pong ball. Now here's one way we could do this. We could teach the baby Newtonian physics. When your paddle strikes the ball, depending on the velocity of the paddle, the elasticity of, otherwise known as the sponge, on the paddle, you will calculate the velocity that the ball leaves the paddle, where it bounces on their side of the table, and therefore you do a very, very fast, relatively simple computation. You simulate the trajectory, and before it enters your space, you will start to swing the ball. That's one method of teaching a baby how to play ping pong. Well, this is the way I learned how to play ping pong. I wish I had started then. I'd be savant now. There you go. Here's the way you teach here's the way you teach a world-class athlete how to play ping pong. What you do is this. You show the baby what it means to play ping pong. So you hit a couple of balls, and then very quickly after that, you put a bat in their hands and you let them smack away. And every time it hits it properly, you reinforce the behavior. Every time, if they repeat bad behavior or the wrong way of hitting, after several times, you show it again what it means is right behavior. Well, it turns out that training a baby how to play ping pong and training a car how to drive may be similar. It may be similar. Now, I know it sounds like lunacy at the moment. Well, it turns out it's not so lunatic. DARPA funded a project called DAVE. DARPA Autonomous Vehicle. The project leaders were two people. One of them, I mentioned earlier, serendipitously, is Jan LeCun. Jan and Urs Müller partnered to develop, were funded by DARPA to create a self-driving car, a self-driving vehicle that had no programming at all. There is simply a deep neural net inside Dave. Dave was trained the behavior of driving. So Jan and Urs is now my chief architect for autonomous driving. Jan and Urs set off to figure out whether that's possible or not. Well, here's Dave in action. Now, the important thing about this is this. What Dave is trained to do is navigate in a very hostile environment, and what it's driving over right now is a very hostile environment. It's finding its own path. There's no programming involved. There's, of course, a very well-designed network that's running inside Dave, but somehow it's finding its own way. It's avoiding collisions. It knows what to drive over. It knows what it can't drive over. Some rocks it can drive over, some rocks it can't drive over. The rubber hose is okay to drive over. The wooden stick is okay to drive over. But some rocks are too big to drive over, like that wall. And it avoids it all by itself. And it meanders along. And in the size of Dave, he's actually moving pretty fast by that scale. All of this was done on just one CPU. They were very computationally challenged. It was trained on large clusters of CPUs, supercomputers basically. And here's Dave in action. Now, it's actually really interesting. This is what Dave was taught with. What Dave was taught was this. Basically, a few 100,000 images, 225,000 images, and it was simply shown an image, and it was also labeled by the human action. What the human did. What the coach did. Shown this image, what did the human do? Shown another image, what did the human do? These are all random objects in the backyard, not the path. This was trained on just some random objects in the backyard, not ultimately the navigation path. You could put it on any navigation path after that. So it's trained by these things. It saw all these various objects, and it was informed by what did the human do? What did the coach do? What is ground truth? What is the right answer? What is the right behavior? It was trained over and over again. Now here's, before it was trained, Dave was not very well informed, runs into that bag. This is trained after 52,000 images. The behavior, the input was images, the output was drive commands. The input was images, the output drive commands. So now it looks at these videos and it does what the human would have done. It looks at these videos, processes it through the deep neural network, and does what the human would have done. And this is fully trained. Isn't that amazing? Deep neural net in action. It is perfect at predicting the expected behavior, the right behavior given a large amount of unstructured data. Deep neural networks are just wonderful at taking large amounts of unstructured data like we do and predicting the right behavior, the best behavior. Now, just to compare it to Drive PX, this is what a Drive PX is. So Dave, you guys saw Dave. Dave is basically completely computed on a CPU. This is Drive PX. Okay? Drive PX is 2 Tegra X1s, about 2.3 teraflops. This is a supercomputer right here in this little motherboard. It has 12 cameras that comes into it. So we could feed it with front cameras. In this particular case, Dave had front cameras. We could feed it with cameras all around us. And based on all of the input of the cameras all around us, we could decide by training this network what is the proper behavior. So if the car in front of me stops, however, depending on what I see in my rear view mirror or what the computer sees in the rear view mirror and the side mirrors, it might decide the best answer is not to stop. It might decide the best answer is simply change lanes. Okay? There are all kinds of things that we could teach the right behavior. We simply have to provide it with a lot of data. And so this is Drive PX. Now just to compare it to, if Drive PX can process AlexNet at 184 frames per second. So the AlexNet is that big, huge network that was shown earlier. Drive PX can process AlexNet at 180 frames per second. AlexNet has, if you can think of it, essentially a brain. This network has 630 million connections, almost 1 billion connections in this brain. 630 million connections. And we can activate those 630 million connections at 184 frames per second. That's basically 116 billion connections per second. That brain is firing off 100 billion times a second. Comparing what you saw was achievable by Dave, that was 38 million. 3,000 times faster. 3,000 times more neural capacity. So the question is, what can we teach Drive PX to do? Drive PX. Our vision of what this architecture is basically to augment today's ADAS systems. If our little Drive PX, if little Drive starts to veer off into the wrong direction because it wasn't taught properly, or its teaching or its learning is incomplete, all we have to do is stop. the ADAS system would simply kick in. It's no different than us treating our kids. We teach it the proper behavior. We send it off. It gets smarter all the time. However, every so often, we tell it, don't do that. That's going to hurt. ADAS system is going to be there for that. To augment today's ADAS system with a deep learning network has enormous potentials. And I'm looking forward to when that happens and the big bang happens in self-driving. All of a sudden, we have amazing cars doing amazing things. And it's constantly getting smarter because we OTA it. Drive PX, our platform for self-driving car computers. It's the most advanced car platform on the planet, car computing platform on the planet. It's available in May as a developer kit, just like Digits, the dev box. We would like you to come to the website, fill out your needs, and we'll get right back to you. The dev kit is $10,000, comes with a ton of software, and it gets you going to build your self-driving